So what we're looking at here is a diagram of ATP synthase, or the enzyme protein that is responsible for generating ATP. You can see that it is divided into two segments. The F1 portion is in the matrix of the mitochondria, and the F0 portion is embedded in the inner membrane of that mitochondria. We're going to take a look at the important parts of this, and then we'll take another look at this in a different view, which is basically a space modeling view in the next slide. But here in the F0 portion, we have an A unit, and we have C 10 through 15. So the hydrogen ions enter an inlet and are transferred then to a protonable aspartic acid residue in the C units. This portion rotates, and when it gets around to this side, the hydrogen ion is released into the outlet channel. So this A unit has two separate compartments, inlet and outlet channels. And again, these hydrogen ions are entering the inlet and are deposited on the outlet side of the what we're going to call the rotor. Actually, this is called the rotor portion. And now the rotation of this ring is then coupled to ATP synthesis. Now, as we look at this next slide, again, this is more of a space filling model. It shows that rotor that is embedded in the membrane, the mitochondrial membrane. There is a shaft that connects the rotor to the business end, let's call this, because this is the catalytic end of this protein. It also has this stabilizing arm called the stator that also anchors it to the membrane. So in the F1 portion of this, we have 3 alpha and 3 beta subunits, and they're alternating in the structure. The beta subunits bind ATP and are catalytic. So what we're looking at here is a depiction of that hydrogen ion gradient that drives ATP synthesis. A British biochemist by the name of Mitchell proposed this theory, or what has become known as a theory. You may have heard it called chemiosmosis, but basically what this is an electrochemical gradient. And Mitchell proposed that this electrochemical energy is stored in the hydrogen gradient across that inner membrane and drives the synthesis of ATP. So the hydrogen ion gradient is essentially equivalent to an electrochemical potential. So let's take a look at the effect of hydrogen ion concentration on that inner membrane. This is the matrix side, this is the inner membrane of the mitochondria. On the matrix side, we have low concentration of hydrogen ion, therefore our pH is high. And this causes a negative charge to set up along the membrane on the inside. On the exterior of that inner membrane, our hydrogen ion concentration is high, therefore our pH is low. And this sets up this positive charge on this side of the membrane. We can actually quantitate the change in free energy associated with this electrochemical potential. And we will do some practice problems as soon as we finish covering the slides in this last segment. But the change in free energy is equal to R, which is a gas constant, temperature in Kelvin, and we take the natural log of C2 over C1, where C2 is the hydrogen ion concentration in the inner membrane space, and C1 is the hydrogen ion concentration in the matrix. Z is the charge on the proton. F is the Faraday constant. We worked with that before. And this symbol is the change in the electrochemical potential or the membrane potential. And as I said, we will do some calculations with this equation after we finish our slides. So what we're looking at now are the thermodynamics of glycolysis. And if you recall, negative delta G's are very favorable and spontaneous reactions. So here in this table we have the standard free energy. Okay. So this would be free energy under standard conditions. The delta G in this column is the change in free energy under cellular conditions. So this is what we're really interested in. I want you to focus on, let's see if I can get a little pointer here, the relatively large, where's the other one? Delta G's, or large negative delta G's in this column. And the first one is associated with hexokinase, which is that first step in glycolysis. The third one is at step 3, phosphofructokinase. And finally, we have, pyruvate kinase, here we go, which converts phosphoenolpyruvate to pyruvate. So these large delta G's tell me that these are very important regulatory steps. So these are highly regulated. Now we can look at that this in a little different form graphically, or table bars. Again, here's the standard free energy. So this would not be cellular. This is the standard free energy in actual erythrocytes. And again, you see at step 1, 3, whoops, sorry about that, and 10, we have large delta G's, which again are points of regulation. Now we're taking a look at the delta G's associated with the reactions in the citric acid cycle. So these two will be points of regulation. The first step is the condensation of acetyl-CoA with oxaloacetate to form citrate. That is highly regulated. We also have isocitrate dehydrogenase, and then finally alpha-ketoglutarate dehydrogenase. These large delta G's also tell me these are highly regulated steps. Here you see these reactions. Delta G's are about 0. That means that these reactions are at equilibrium. So the forward and reverse reactions are occurring at the same rate. The only thing that will change this activity is concentration of a reactant or a product to force it in the other direction.